So I want to look at another example of solving an exponential equation, and this time it's going to be a story problem or an application problem. So we are told that a plankton population is modeled by the exponential function p of t, which is equal to 1,000 times e to the power of 0.00578 times t. The output of our function, or p, is measuring the number of plankton in a cubic meter of seawater, and t is representing time measured in minutes. And so what we're trying to do with this model is figure out and predict how long it takes until the population of plankton reaches 1 million plankton per cubic meter of seawater. So I think this is a really cool application with some real world value, because if you know some things about plankton, one of them is they're basically the bottom of the food chain, and they're eaten by things like shellfish and other filter feeders, and those shellfish are then eaten by larger organisms like humans and other mammals. But what happens is if these shellfish eat certain types of plankton, then the chemicals and toxins in those plankton get accumulated in the fat and the tissue of those shellfish. And then that can be a really concentrated amount of toxins or chemicals that is then consumed by a larger organism like a person or a whale or whatever ends up eating that creature that was eating the plankton. And so monitoring plankton populations can be really important to kind of predict when these kind of events are going to occur. And if you've ever watched the news and heard of something like a red tide or a harmful algal bloom, that's essentially what they're referring to. So monitoring and being aware of when a population of plankton kind of reaches a critical point can be really helpful for knowing when you have to tell people to stop like farming shellfish or going to the beach and things like that. These numbers are just made up though. I'm not sure if it actually takes 1 million plankton or if it's more or less for a harmful algal bloom to kind of come into effect. But really in the end, this is just getting more practice solving an exponential equation. So if we want to figure out the answer to this question, we have to figure out when is the number of plankton or the output of our exponential function equal to 1 million. And so that's going to give us the equation 1,000 times e to the 0.00578t is equal to 1 million. And so we're going to use our same process for solving exponential equations that we've used in our earlier examples, but there's one little twist to this one, and that's that our exponential function is not entirely by itself at the start because it's multiplied by this number of 1,000. And so we can't convert this easily to its logarithmic form until we get rid of that number of 1,000 out front. But that's really not too bad to do because we can just divide it away. So if we divide both sides of our equation by 1,000, we end up with our exponential e to the 0.00578 times t is equal to 1 million divided by 1,000. Well, we can simplify that to 1 million divided by 1,000 is 1,000. And so now that we have our exponential isolated on one side of our equation and it's equal to just another number on the other side, we can convert it to its logarithmic form and make progress towards solving. So what is the logarithmic form of this equation going to look like? Well, the base of our exponential is e, so the base of our logarithm has to also be e, so that means we're working with a natural log. What goes inside of our natural log is what our exponential function is equal to. So that is 1,000. And then what our logarithm is equal to, or what comes out of our logarithm, is our exponent, and that involves the variable we are trying to solve for. So this is giving us the equation, the natural log of 1,000 is equal to 0.00578 times t. And now we're just one step away from finding the exact value of t, or how long it takes for our population to grow to 1 million plankton per cubic meter of seawater. We just have to divide the natural log of 1,000 by that decimal in front of t. So we got the natural log of 1,000 divided by 0.00578. And so when I entered that into my calculator, I got a value of approximately 1,195. And remember, our units for time here are minutes. So it takes about 1,195 minutes, rounding to the nearest minute, for this plankton population to grow from 1,000 plankton to 1 million plankton. And maybe thinking of a large number of minutes is hard to kind of digest or make sense of, so let's go ahead and convert that to hours. So if we take 1,195 minutes and multiply that by the conversion factor that says there is 60 minutes to every hour, or 1 hour to every 60 minutes, then we see that we can convert 1,195 minutes to hours just by dividing by 60. And if we do that calculation, we get a value of approximately 19.9 hours, or 19 hours and 54 minutes if we want to convert that little leftover hour to minutes. And so in under a day, this plankton population can go from 1,000 plankton up to 1 million plankton per cubic meter of seawater.